Good afternoon and welcome to the CERIAS Security Seminar from Purdue University. Our speaker today is a senior PhD student working here with Professor Arif Ghafoor in our Electrical and Computer Engineering Department, Mohammed Umer Arshad. His topic today is trust management for publishing graph data.
Good afternoon, everybody. Thank you, Andy, and thank you for the opportunity to come and speak at CERIAS Security Seminar. As some of you might know me, my name is Mohammed Umar Arshad. I'm a PhD student in ECE department. I must admit that I am not a computer security and cryptography guy. So previously, during my PhD, I have worked in the problems related to database systems, parallel data systems, performance evaluation, query processing and optimization, and resource management schemes in distributed systems. The work which I am going to present today has been done in joint collaboration with Ashish Kundu at IBM Watson Research Center and Professor Alisa Bertino. So just to start with, in this talk, we will not be touching the privacy aspects. So we are just dealing with the security of data, and we are actually dealing with the security of a specialized kind of data structure, graph data. And when we talk about security, we will be actually dealing with trust management, which falls under the umbrella of the security. So the outline of my talk is as follows. Motivation, what is the motivation of my current work, and what was some related work, what are the main contributions which we made, and then I will describe our main contribution, Cloyan resistance hashing for graphs and perfectly Cloyan resistance hashing schemes for graph, and at the end some performance results for our experiments and algorithms. So motivation. So as we all know that graph structure data and models are on the rise in graph databases in biological and healthcare data, as well as modeling system and network topologies and social networks, for example, friendship, collaboration, and correspondence. So it is a very prevalent and very commonly used data structure. For example, if we talk about Facebook, LinkedIn, etc., Twitter. So basically, these are all graph structured data which connect different communities, different groups. And in this data structure, there are nodes and edges, and there are different kind of relationships between those nodes and entities. So let me give you a motivation scenario for my work. So we are here talking about a particular scenario where we use internet services like platform services or software services over the internet. And we are all familiar that in cloud computing there are such services present as platform services, software services, or hardware services. So it is very common for the owners of the data to actually give their data to some third party to publish that data online, to use their services or to use their softwares. So ultimately what happens, the users on their side, they actually run queries and they try to retrieve their data from those third-party servers. And those third-party servers actually process the query and return the required result to the user. Now there is this issue that those third-party servers or third-party services, they may be compromised and the result which is ultimately returned to the user, it may be forged. So when we talk about the integrity of data, here in the trust management, we are talking about the integrity of the data. So by integrity of the data, we mean that once a user has received the result from third-party servers, so how he can be assured that this data has not been forged and this data is complete? By forging of data, when we talk about graphs, basically there are two things: the content of the data and the structure of the data. So we all know that in graphs there are vertices, and those vertices are connected through edges. So it is quite possible that the untrusted server may forge this data, and there is this possibility that the content of the graph itself is changed. So for example, the data which is present in the vertices are nodes of a graph that may be forged, that may be changed. And also it is quite possible that somehow the structure of the graph may also be changed. So somebody there may remove some edges or add some edges, and similarly remove some vertices and add some vertices. So the user, at the user side, the users want to be assured that the query answer which I have received from the third-party server, or the results which I have received, that has not been forged. So it means the content and the structure of the result which a user has received, that is intact as present in the original graph, or the original data which was present at the untrusted server. So integrity verification, when we talk about integrity verification of graph data, so we are actually talking about two main things: the content of the graph and the structure of the graph. So in this paper, the focus is to develop some cryptographically secure hash schemes to hash these graphs so that both the content and structural integrity of the data is not violated. The other thing which is of interest is the integrity also encompasses this concept that the data which a query returns, that is complete. Complete means, so for example, if you run a query against a graph database, and that query should return n vertices and m edges, so the complete result is returned by the server. The server does not retain some of those x vertices and y edges. So hash functions are used towards the verification of integrity and digital signatures, and they are the fundamental building blocks of all modern crypto systems. Traditionally, when we talk about hash functions, basically we have a string of length n, and then hash function basically compresses that strings and outputs another string, which is a compressed version of that input string and whose length is less than n. So traditionally, the hash functions basically compress the input string and generate an output string, which is a compressed version of the original input string. But when we talk about graphs, in graphs we don't have strings. We have vertices, and then there is relationship between those vertices in the forms of edges and links. So this problem becomes a little bit challenging, that how you can actually compute the hash of a graph. So therefore, the problem of hashing graphs with respect to crypto systems need to be studied and addressed. Traditionally, a very common data structure which is used for hashing trees is the Merkle hash technique, which was presented in a research paper in 1989 by Merkle. But people have used Merkle hash technique to hash trees, but this Merkle hash technique cannot be used for graphs, because graphs are more complex data structures. So I will elaborate on this concept in my later slides. So hashing graphs poses several challenges. As we know, graphs have several nodes and edges, with each node having multiple incoming edges and outgoing edges. The edges may be directional, and there may be cycles in the graphs. There are 4 types of graphs that are of interest in this paper or in this presentation: trees, directed acyclic graphs, graph with cycles, and graph with multiple sources. So any questions so far? I will briefly go through some related work. So 2 of the most closest techniques which are related to our work are Merkle hash technique and search DAG technique. So search dash technique is a variation of Merkle hash technique that uses Merkle hash technique as its underlying mechanism. So what is the Merkle hash technique? So a Merkle hash is a basically bottom-up mechanism to compute the hash or digital signature value of a tree. So if we have a node x in a graph, so the Merkle hash of that node, if the node x is a leaf node, the Merkle hash of that node is computed as the hash of the content of the value which is in the leaf node. Otherwise, if it is some internal node or root node, so it is the concatenation of Merkle hash of all the children of that node, and then we compute a global hash of that concatenated hash value of all the childrens of the internal node. So let me explain this through an example. So if we look at figure A, so E and F are the leaf nodes, so we can compute the Merkle hash of E and Merkle hash of F by hashing the content value which is stored in the internal representation of these nodes. Once we have the Merkle hash of E and Merkle hash of F as computed, so we can compute the Merkle hash of D as the concatenation of the Merkle hash values of E and F, and then computing the hash value of that computation, hash value of the concatenation of nodes E and F. So here you can see that. Similarly, to compute the Merkle hash value of internal node B, we will need to have the Merkle hash value of D, and to compute D, we will need the Merkle hash value of nodes E and F. So basically, this is a bottom-up procedure to compute the hash value of trees. But we cannot apply these techniques for graphs, because in graphs we can see that there can be different kind of edges. So there can be some forward edges, which I will elaborate, some backward edges, and some cross edges. So because of those forward, backward, and cross edges, the traditional Merkle hash technique cannot be applied to compute a global hash values or a global signature of the graph. So let me step back. In fact, I forgot to tell you the focus of this presentation. So here we are trying to address a specific kind of graphs. We are dealing with directed graphs, but those directed graphs which have cycles and which may not have cycles. So when there are cycles in the graph, so they pose several challenges. And basically, we can categorize the edges in a directed graph in 4 different kind of edges: tree edges, forward edges, cross edges, and back edges. So because of these forward, cross, and back edges, we have different cycles in the graph, and those cycles basically did not allow the traditional Merkle hash technique to be applied to directed and undirected, directed cyclic and acyclic graphs. So basically, in this research, we propose some schemes, so how to tailor or how to modify the structure of these directed graphs, which have cycles and which don't have cycles, and to modify that original input graph so that we have a resultant graph or resultant data structure, which we will elaborate in later slides, which we call that efficient tree of that input directed graph. And in that efficient tree representation, we have actually taken care of all those forward, backward, and cross edges. So I will skip the previous 2 slides. So what actually happens in Merkle hash computation of trees, that there are some privacy breaches and there can be some privacy attacks which can be executed on the Merkle hash which is computed on a tree. So when a user runs a query on remote server and remote server returns the results to the user, in terms of graph, what is the result which is returned to the user? When we talk about graphs, the result which is returned to the user is actually a subgraph. So basically that subgraph is returned to the user, and under this third party scenario, for the user to be able to verify the integrity of return result, the third-party server actually also returns to the user a set of verification objects. That set of verification object is actually a set of vertices and edges which is not part of the result which is returned to the user. So that part of graph which is not returned to the user as part of a query result, we called it a redacted subgraph, or we use this terminology redacted graph. So the third-party server computes a set of verification object or some kind of verification information which is also sent along with the query result to the user, so that user can use both the return results and the verification object to verify the integrity of data. So in case of Merkle hash technique, I will not elaborate that and go into detail. There are some privacy breaches that once a user actually receives his subquery result, so he can actually execute some privacy breaches and he can execute some privacy attacks. So when we talk about a graph, so based on the subquery or subgraph results which the user has received, the user can actually infer some other information about some other nodes and some other links which were not part of his result which the user has received. So how actually we can develop some schemes that user actually is not able to infer some other nodes and some other links information which is not part of his results. So we will address those issues in this presentation. So what are the main contribution we made in this work? We define the practical and formal security model for hashing schemes for graph. We define the formal security model of perfectly secure hashing scheme for graphs. I will elaborate by what does it mean for a hashing scheme to be perfectly secure. And we describe the construction of hashing and perfectly secure hashing schemes for graphs. And at the end, we show the performance results for the construction. So here I want to mention that these are the first schemes proposed by us to address directed graphs which have both cycles and which don't have cycles to compute hash value of these kind of graphs. We don't need to go into much detail into mathematical proofs and mathematical definitions of hashing scheme, but just briefly, so a standard hashing scheme consists of two probabilistic polynomial time algorithms, gen and hash, satisfying the following requirements. So basically these algorithms have two sub-algorithms or functions. One is the key generation, where a random key is generated using some probabilistic key generation algorithm. And then for computing the hash, we use this random key which is generated in the first step to compute a hash of the input string. So for example here, x is the input string, hash is the hash function, and to that hash function we give that random key which was generated in the first step to compute a string which is a binary string and whose length is L, and lambda is a security parameter which is implicit in the key generation of the random key. So usually whenever some hashing function or hashing scheme is developed, so there is this collision finding experiment. So what do we mean by collision? So if we have two different strings or if we have two different values and we compute their separate hash functions or we compute their separate hash values. So if those values came to the same output compressed string, it means there is a collision. So a good hash function should be such that the probability of two different strings having the same hash computation value should be negligible. In fact, I am using this term negligible in a very loose term. In cryptographic, this is very critical that no two strings under some cryptographically constraints should end up having the same hash value. So we call a hash function collision resistant if for all probabilistic polynomial time adversaries there exists a negligible function such that the probability of hash collision is 1 and this probability is less than negligible function. So let us don't go into detail of this mathematical explanation. So we use this basic definition of standard hashing scheme and we come up with formalism for collision resistance graph hashing scheme. So how we can use this standard graph hashing scheme for collision resistant graph hashing scheme. So a graph hashing scheme basically consists of 4 functions: generate, hash, graph redact, and graph verify. So of these 4, these 3 functions are probabilistic or randomized algorithms, and the last one is the deterministic algorithm. So basically in all of these schemes, the first part is the key generation algorithm. So we generate a key which we give as input to hash function for computing the hash value of a graph. And the function which generates that key is generates that key using some random function or using some random computation. That's why this is called a probabilistic key generation algorithm. We use that key which is generated in the first step and we give that key as input to this hash function, and here you can see that to this method we are actually passing a complete graph which consists of a set of vertices and a set of edges, and ultimately this function returns us a binary representation of the hash of that graph. So when we talk about graph hashing schemes, so there are 2 more methods: graph redaction and graph verify. So just in simple layman terms, the redacted graph or redaction of a graph is that part of a graph which is not that part of graph that is not returned to the user. So we have an original graph G, and to the user we return as part of subquery result a subgraph G dash. So G minus G dash, that part of the graph which is not part of the subquery result which is returned to the user, that is known as a redacted subgraph. So why we need redacted subgraph? As I explained to you earlier, that when the result is returned to the user by the third party agent, so the third party publisher also returns to the user a set of a verification object. That set of verification object along with the query result which is received by the user is actually used to determine the integrity of the complete data. This graph verification function is actually executed by the user on the user side. So the user on its behalf has a graph hash value which is the original hash value of the complete graph, a set of subgraphs which are returned as part of the query result, and a set of verification object which is returned by the third party publisher to the user to verify the integrity of the data. So how we can verify the correctness of these schemes? So basically formally there are these 2 mechanisms: hashing correctness and hash redaction correctness. So the first thing is called empty redaction. So suppose a user runs a query where the query result is the complete original graph. So in that case the user receives the complete original graph as part of subgraph, as part of the query result, and here we can see if we compute the redacted graph, that redacted graph will be an empty graph. So the verification object set which is returned to the user as part of the redacted subgraph will be empty. So if we compute the when we execute the verification function at the user side, the output will be 1. The other is the hash redaction correctness. This is the other case where the user is retrieving a subgraph as part of the query result, and we compute a redacted subgraph, and using that redacted subgraph, we compute a set of verification objects. So on the user side, the user has on his side three things: a set of subgraphs, a verification object set, and the hash value of the original graph. So he uses all these three values, and if the output of this function is 1, so it means that the data has not lost its integrity. So let me skip this Klein finding experiment, and let us move to this perfectly Klein resistant hashing of graphs. So what do we mean by perfectly Klein resistant hashing scheme for graphs? By perfectly, we actually mean that when there are some hashing schemes, and when those hashing schemes hash some values and they compute a compressed scheme or a compressed string of the input string, it is quite possible that there are some security attacks which can actually determine the length of the input string, and based on that length of input string, they can determine the input. They can determine some information about the input which was being hashed. So in case of perfectly secure schemes, what actually happens that another random key is generated as part of the hashing function, and this mechanism ensures that the user is not able to infer any information about the length of the input strings or about the length of the input string in case of string or text data, or about the content of the graph which was being hashed. So once again, when we talk about perfectly secure graph hashing scheme, so there are 4 functions: perfect graph hashing scheme generation, perfect graph hash redaction, and perfect graph hash verification. So we can see here that here we generate 2 random keys, S and R, and we use 2 of these random keys, S and R, and we pass those keys to a perfectly secure hash function H, and this hash function takes as input a graph G, and it outputs a hash value which is some digital signature of that complete hash graph. This hash redaction function is similar to the previous hash redaction, that redacted graph is that part of the graph which is not returned to the user as part of the subquery result. This hash verification function, it is again similar to the previously discussed hash verification function, is executed by the user on the user side. So the user has the hash value of the original graph. It has a set of subgraphs which are returned as part of the subquery result, and it has a set of verification object. So on the user side, the user uses this information to actually compute a value. If that value is 1, the user is assured that the integrity of data has not been violated. Once again, I will skip this Klein finding experiment. And now comes a little bit interesting part of the talk. So there was a lot of mathematics in the previous slides, and I know this was a little bit dry, but I will take a pause here and let us have a few questions. Before going to a later part of my talk, let me go back again in one of my earliest slides and diagram. So in this diagram, basically there are 3 entities. There are users. Users actually want to retrieve some information or some data which is stored on some server over the internet, and we say that this server is actually storing that information and that data and that server is untrusted. So that server can be compromised. On the other side, that server can in fact forge some data. So we can see here there are some data owners. Some data owners actually pay to these service providers to publish those data, to publish their data or store their data and information on the hardware and software services which are being provided by third-party data distributors to publish their data. So basically the owners of the data just give all of their data to some third-party data publishers, and they pay them that if users are trying to retrieve some information, that you take care of this data storage and security and etc., software configuration, installation, etc., on my behalf. So the users actually issue the queries. So what happens, these third-party servers actually publish the data. So there can be multiple users who actually issue the query to this third-party server. The third-party server actually processes that query and returns the output as part of subgraph to the user. So here we can see that this third-party server actually returns a subgraph and a set of verification object. So when I say verification object, so verification object is a set of vertices and edges which we compute using the redacted subgraph. Redacted subgraph is that part of the graph which is not returned to the user as part of the subquery. So the user on its side runs this algorithm, graph verification. So user receives a subgraph from this server and a set of verification object. To compute this verification object, this server actually runs a function which is known as graph redaction algorithm. So this algorithm is run on the server side. So these two things are sent to the user by the server, and the original data owner has actually a value which is known as the hash value of the complete graph. We can consider it some kind of key or some kind of certificate that we can compare against to verify that this data has not been forged. So this is the big picture, and in this paper, as I discussed, that we are dealing with specific kind of graphs which are directed graph, and those graphs can have cycles and those graphs cannot have cycles. So we are not dealing with general graphs where we can have undirected edges. So that problem is more complex, and that is not the focus of this current work. So here is the secret sauce which we use to develop these algorithms, how to break the original structure of a directed graph which has cycles and which don't have cycles, to develop a new data structures which we call efficient tree. So let me ask you, how many of you have taken algorithms course? Okay, very good. So in the algorithms course, the most fundamental algorithms are breadth first search and depth first search algorithm. And if you have interviewed for some of the software companies, so the most commonly asked question is, what are different tree traversals on these graphs? For example, pre-order traversal, post-order traversal, in-order traversal. So if you go back to Corman's Computer Introduction to Algorithms book, and you study this algorithm, depth first search algorithm, and once you run those depth first search algorithms, so that algorithm classifies the directed edges of a graph into 4 types of edges: tree edges, forward edges, cross edges, and back edges. So basically the scheme which we use, that we have at our on our side or at our hand a directed graph. So we run depth first search algorithm on that directed graph. And during that depth first search algorithm, we assign pre and post processing numbers to each and every node of a graph. So once we assign those pre and post processing numbers to each and every node of a graph, so we can use this information to actually break the structure of the original graph. So there is a lemma that the pair of post order and pre-order numbers for a node in a non-binary tree correctly and uniquely determines the position of the node in the structure of the tree, where the position of a node is defined by its parent and its status as the left or right child of the parent. So this is a very interesting result. Some graph theoretician produced these results that if we assign pre-order number and post-order number to each and every node of a graph, and then we break that graph, it means we have only set of vertices. So we can then use that information which is stored inside the vertices of that graph to in fact construct the original graph. So just remember that when we are doing this depth first traversal and we are assigning pre-processing and post-processing numbers, so we have four kind of edges: tree edges, back edges, forward edges, and cross edges. Actually, what we want to do, why we are assigning pre-processing number and post-processing number to the vertices of the graph. So the job we want, the task or the target we want to achieve is to modify the original directed graph into another graph where we don't have these forward, cross, and back edges, but we have the tree edges. So we want to have a mechanism where I have transformed the original graph into another graph. And in that other graph, I don't have forward, cross, and back edges, but somehow I have some additional information stored in that new graph that if I use that additional information, I can reconstruct the original graph. So this way, from a directed graph which has cycles, I construct a new graph, which is again a directed graph, but which is without forward, cross, and back edges. So it means in the new graph, we don't have cycles. So if you assign pre-processing number and post-processing number, so you will see that the post-order number of a node is always smaller than that of its parent. The pre-order number of a node is greater than that of its parent. The in-order number of a node in a binary tree is greater than that of its left child and smaller than that of its right child. And a specific traversal number of a node is always smaller than that of its right sibling. So let us go through an example. So here we have a directed graph which is composed of 7 vertices, G1, G2, G3, and up till G7. So if we assign the pre-order numbers, so pre-order number, when you run depth first search algorithm, so basically it is a pre-order number of, it assigns a pre-order number to the vertices of the graphs. So the pre-order number of vertices G1 to G7 are assigned like this. Vertex G1 is assigned a pre-order number 1, G2 is assigned number 2, G3 is assigned number 3. So the recursion is going in depth first manner. Then at G3 we have 3 children, so we go to G4, it is assigned as number 4. Then we go to G6, it is assigned number 5. Then we go to G7, it is assigned number 6. And then we traverse back, and G5 is assigned number 7. This middle column is for post-order numbers. So post-order numbers are assigned. You can see here in this diagram that the post-order number of G7 is 1. So we started depth first recursion starting from node 1, and we went all the way up till the root. So there was no recursion beyond that level. At that level, we assigned the post-order number value of 1 to this vertex V7. So by using a depth-first traversal of a directed graph which has cycles, we assign both pre and post order numbers to each and every vertex of that graph. So once we have this information available with us, we can actually decompose and break the structure of the graph. Now here we can see that there are 4 kinds of edges. So there is this edge which is going back. This is called back edge. There is this cross edge, and then there is this forward edge. How we can determine that this is back edge, this is forward edge, and this is cross edge? And there are these edges which are called forward edges. This is a very standard material which is present in Corman's book. Actually, we can use these post order number and pre order numbers to determine whether an edge is forward, cross, back, and forward. For example, for the tree edge, let OX and QX refer to the post order number and pre order number of a node X respectively with respect to depth first search tree. So it is a tree edge if the post order number of X is greater than the post order number of Y, and the pre-order number of X is less than pre-order number of Y. Similarly, there are some other rules using which we can determine forward edge, cross edge, and back edge. So once we have this information, actually we can decompose the original graph. So let us now look at this diagram. So suppose I have this original graph available with me. In this original graph, I run depth-first search algorithm, and I assign both pre-order and post-order number to all the vertices. Now in this graph, we can see the edge from B to C, a B to F, this is a forward edge. So using the pre and post order number of node B and pre and post order number of node F, I can classify this edge as a forward edge. So once I classify this edge as a forward edge, so I can actually remove this edge from the original graph, and I can create a new graph, and in that new graph I create a specialized node which I called, for example, a super node, and then I create a new edge from the original or source node to that super node. So this super node, which is basically a forward edge from node B to F, this contains information about the pre and post order numbers of both the source and destination. So this way we can see here in this figure B, this edge which originates from C up till F, this is a cross edge. We can classify this as a cross edge. So what happens in the original graph, we remove this edge and we create another specialized node called super node with the name CE, and I create a new edge which I call and I create a new edge from that source node up till that super node. So once this new tree is generated, we can see that in this new tree now there are no cycles. So these cycles were basically because of these forward edges and cross edges. So once I have this updated tree, which is basically a directed tree, but in this directed tree I have removed forward, cross, and back edges, but this updated tree inside these super nodes contains that information in the form of pre and post processing number. I can actually use this information to construct the original graph. So using this directed tree, once again the next step is that we want to create just a two-level data structures which we call efficient tree representation of this directed tree. As we might recall from our previous slide, that Merkle hash technique is basically a bottom-up technique which computes the hash value in a bottom-up fashion. So here basically we create a data structure which is just 2 levels deep, and we arrange all of these vertices, whether they are the original graph vertices or the newly created vertices which we call super nodes, and we arrange them maybe in some pre and post order fashion, And using this newly created data structure, we compute the hash value for the original graph. So this was the basic scheme which we used in our algorithm to take care of the cycles in directed graph and how to compute the hash value of those graphs which have cycles inside them. These are the algorithms, so I will not go line by line into their detail. So there are three algorithms. The first algorithm is to compute how to compute the hash value of the input graph. I just explained to you that we have a graph. So using pre-order and post-order numbers, we remove forward, cross, and back edges, and we create a new graph, which is a directed graph. And inside that new graph, we have the information of pre- and post-order number of each the node encoded. So using that newly created directed graph, we create another two-level data structure which we called an efficient tree, which is a two-level data structures or a two-level tree. And once that efficient tree is generated, so then we can use the standard Merkle hash technique in a bottom-up fashion to compute a global signature value or a global hash value of the original graph. As I explained to you what we do in graph redaction algorithms, so when a query of a user comes and user is returned a subgraph, so the graph redaction algorithms computes that part of the graph. It means it tries to determine those vertices and edges which were not part of the graph, and it generates a set of verification object, which is also sent by the third party untrusted server as part of query result to the user. So this process or this algorithm that how to compute a redaction of a graph and generate a set of verification object is known as graph redaction algorithm. The next, the last algorithm is the graph verification. So this algorithm is run by the user on his site. So user has three things with him. So he has the global hash value of the graph. Then from the third party untrusted server, he has a set of subquery results and he has a set of verification objects. So the user uses all these things and he computes another hash value, suppose gh dash, and then the user computes that gh dash or a newly computed hash value with the original hash value gh, which was sent to the user by the data owner. So if this value is same, the user is assured that the integrity of the data has not been violated. Once again, when I say about the integrity of data, so in graphs there are vertices and there are edges. So we want that the content which is stored inside the vertices, that has not been modified, and the structure of the graph has not been modified. By structure I mean nobody has added or deleted some vertices and edges of the graph. If somebody has tried to forge or change either the content or the structure of the graph in the query result which is sent to the user, so this condition will fail and 0 will be returned. So the user has a mechanism to verify that the result which I have received, that is not true, or somebody has forged this information. So as the main scheme or the main mechanism underlying our algorithm is graph traversals, and when we talk about graph traversals, mostly they are order V plus E complexity algorithms, number of vertices and number of edges. But it is a little bit more detailed than that, and I don't want to go into detail. So to actually evaluate and test the applicability of our algorithms and the scalability of the algorithms, so we used some real-world data sets which are available on Stanford large graph library. So for example, here you can see that this web Google graph has almost 875,000 vertices and it has almost 5 million edges. This was the largest graph on which we ran our algorithms. So in my performance results, basically we conducted three kind of experiments. So on the user side, user computes the hash value. So when the user computes the hash value, so we first of all generate a tree which we call efficient tree. And once that efficient tree is generated, so using that efficient tree, we compute the hash value of the original graph. So this green bar is the efficient tree generation time, where we assign pre and post processing number and break the structure of a graph and construct an efficient tree. And this red bar is actually the graph computation time. So here you can see in all of these graphs, this hash computation time, this goes up. This is large compared to the efficient tree construction. So yeah, basically what happens, as you remember in the Merkle hash technique, so we go on computing the hash value of all the nodes in the efficient tree, and then we go on concatenating, and that concatenation generates a very large string. And at each step, so iteratively or recursively, that strings goes on increasing, and we have to compute a hash value of that string. So the larger the graph is, the larger the time to compute this hash computation. So here we have three graphs. This hash computation, this is for standard hashing scheme for graphs, and then there are these two graphs. They deal with perfectly collision resistant hashing scheme for graphs, where we generate or add another key, and here we can when we generate a random key, that random key has a length. So here we have two experiments where one of the key has length 128 bit and the other key has length 256 bits. So we can see that as we increase the key length, the efficient tree computation time also increases. In this second experiment, so basically what we are doing, so I am changing the graph size on the x-axis. So it means a graph is, as we are going along the x-axis, the number of nodes and vertices are increasing, and along the y-axis we have the computation time. And I am plotting three functions or three values: efficient tree computation time and hash computation time. And the G hash is the total computation time, which is the topmost bar, which is basically the sum of the lowest two bars. We can see that again in case of perfectly hashed scheme, as we go from left to right, this time to compute these values along the y-axis, they goes on increasing. So for example, here the time is approximately 30 seconds, and here we can see that it is 70 seconds. Here it is 50 seconds. So because of that other random key generation, it has itself an internal computation cost, so that increases the time to compute the hash value. This is the another set of experimental results. So this is the graph redaction time. So we know that this graph redaction function, this is run by the untrusted or third-party server. So basically, if the subquery size which is returned to the user, if that subquery result is very small, it means that untrusted server has to compute a redacted graph which has a very large value. So we can see here that these are the number of subgraph nodes, maybe 10K, 20K, 30K. These are the subquery result size which is returned to the user. But we can see that for the smallest subsize, the time to redact is the highest. This is because so redacted subgraph is actually the other part of the graph which is not returned to the user, and on the third party agent had to do a lot of computation. And we can see that this trend in all other graphs, that as we increase the subquery result size, the redacted subgraph time actually goes on decreasing. And this is the last set of experimental results, the verification of the integrity. This is being run on the user side. So user has the hash value of the original graph, it has subquery results, and it has a set of verification objects. So as the user, we can see along the x-axis, this is the subquery result which a user is receiving. So as the subquery result size is increasing, the time to compute or time to verify the result, it is also increasing. This is because as part of this algorithm, when the user receives a set of verification objects from the third-party server, so on the user side, the user recomputes the hash value of the nodes in that redacted subgraph. So that computation involves some time-intensive operations. So what is the future work or extension? So when we talk about graphs, we have computed, as we know, graphs are very large. Scalability is an issue. And once we have computed a graph, it is quite possible that graph is updated. So are there some mechanisms that if some nodes are added and deleted from that graph, so that we don't have to run these algorithms which are very time consuming to compute an updated or global hash value of that graph. So we did some initial work along this line, but so far our results are not crystallized. That is our future line of research. So thank you. With this, I come to an end of my talk, and please, if you have any questions, please feel free to ask.
Thank you.